Hello, this is Timothy with Growling Pigeon Studio, and today you get to look at my face and listen to me ramble. I want to talk about classes versus structs. I'm going to really kind of focus more on the struct. I don't have a coding example for you or anything, that's why you're looking at my face. And I really want to talk about two aspects of the struct. I want to talk about memory, and I want to talk about performance. All right, so if you went to an advanced high school, or if you took an undergrad in computer science, uh, you may have learned that a struct is faster than a class in C# because it is on the stack. Yeah, I mean, every struct eventually or originates on the stack. You know, you create it and it is created on the stack and returned from the constructor, right? But does every struct remain on the stack? I would say no. I'll give you a couple of examples. First, if you did such a course, undergrad in computer science, then you probably created my list at some point. And my list, of course, has an array inside of it that is of some length that you call capacity. And you also had some counter that would be your count, how many items are in that list. So you add an item, create it in memory somewhere, add the pointer to your internal array of my list, and you increment your count. Create another item, say that now your capacity is 2 and you've reached capacity, right? So you have 2 slots in your array and both slots are filled with pointers. So now you add a third item. Create in memory somewhere out there, you get a pointer to it, and you try to put that pointer in. Well, it says, hey, no, you can't do that. Our capacity has already been reached. You're going to have to double the array. So you have a helper method that creates another array that is twice the capacity. You copy everything from the old array into the new array, and then you add the new pointer. Copy isn't so bad. When we're dealing with structs, things are a little bit different, right? We have some memory that we've put on the stack, that is our struct, and then when we put it into our array, how does it do that? It doesn't get a pointer to it, right? Because our stack is eventually going to go back up, as we take the stack frame off and return to the calling method. We're going to lose anything that was there. It can be overwritten, but that struct needs to stay the same. Well, that means that all that data is copied from the stack and placed into my list. Interesting. So if you have a struct, for example, that is 2 ints, then each slot in your array is no longer a single pointer, which is about the same size as 2 ints in 64-bit architecture, but rather you are placing the 2 ints in a slot, and you have your struct. Now, a struct that is in memory like this takes up less space than a class for one very simple reason, and that is that when you create a class, you have a class instance somewhere out there in memory, you get a pointer back to it, right? That pointer has to be stored somewhere. That pointer is also just a number. Wouldn't that be considered a struct as well? Just another example of structs that aren't necessarily on the stack. So that pointer is placed somewhere, and if you have multiple pointers to the same object, that means that you have all these pointers out there that are taking up memory that go to that class. So a class that has a single int in it, right, could take up who knows how much memory based on how many pointers there are back to it. All right, so here's another example. Say that you have a class that has an int in it. Well, did you know that in C#, an int is a struct? And that int is part of the class's memory. It's in the class. So when you have your pointer and you go to your data, there it is, in memory, not on the stack. And then there's one more place that structs can find themselves, again, going back to the example of an integer, it can fit on a register inside of your processor. So the entire struct can be there. Say that you have 3 ints that represent your struct. Can all fit in the register all at once. Or sorry, not one register, but all in the processor. My mistake. Well, cool. So lots of examples of how structs are not on the stack. They all start on the stack because that's where the constructor puts them, and then we copy it to wherever we're doing our work. But I would say that even though they're not on the stack, they are still faster than the class. And I say that for one really, really cool thing, and that is the L1 cache. Whenever we are running some code, we grab a block of it and load it all up into the L1 cache and then run that code from the L1 cache, right? Well, when we do that, we do that so that we don't have what are called cache misses. We don't do just code, we also do memory. So if we have an array of structs that are all ints, say a single int struct, so we have an array of zeros, for example, the data is all zeros, it's all ints, and we pull up a block of memory into the L1 cache, then we can just work on that really fast. It's right there in the processor. When we get to the end of that block, then we get a miss. We have to go and query the L2 cache, which may or may not have it. We query the L3 cache, which may or may not have it. And if none of them have it, then we go to actual memory and pull it back from there, which takes a long time. I mean, going into actual memory is a lengthy process. So we have our struct. It just loads right up into L1 cache. Cool. Our data is right there. We can just work with it. But when we have a class, we have a pointer to it. So if we have an array, again, and this array of pointers to such and such class that only has one int in it, for example, and they're all set to 0, same example. Well, what happens is we get that block of memory of pointers into the L1 cache. We look at the pointer and say, okay, let's go get that object. That's not necessarily a part of the block that has been pulled into the L1 cache. It could be a part of another block that has been pulled in previously, but it is not necessarily a part of the L1 cache. And it's certainly not a part of the block that we're looking at if that block is entirely full of this array. So that means we get an L1 miss, L1 cache miss, right? Look in the L2 cache for that object, but because it can be stored anywhere in memory, and because garbage collection can move it anywhere in memory, it means that our data for that class could be anywhere. And so we may have to go all the way into memory to get that class data and bring it back up. And that's on the first pointer. All right, well, maybe we get the next 2 or 3 classes with that block load. That would be really neat, but it's not guaranteed. That second object could be somewhere else entirely in memory. And so now we ask for it, and the pointer says, hey, you got to go back to main memory. And it goes, does its thing, and it's a real hassle and gets the memory for our instance. This takes a lot of time. People don't really think about that time of traversal and what an L1 cache miss really means as far as performance. But what it really comes down to is we can write code using structs in an array that is 4, sometimes even 5 times faster than when we're dealing with classes. That may not seem like a lot, but if we're running a video game, especially where we have lots of objects in our scene and we want to be dealing with all those objects, having those objects defined as structs is a very good thing. It means higher performance, and it means we can stuff more objects in our scene, assuming we have the memory for it. If we're using classes and we have that array that we need to iterate over, then we're constantly getting L1 cache misses, and we have to keep going back into main memory to do our processing. Anyway, This has been a short discussion about classes versus structs, focusing primarily on memory and performance. I hope that you enjoyed this little presentation, and until next time, you have fun.